Hello everyone, welcome to this lecture in the Decision Trees from Scratch series. Today, we are going to start building an entire regression tree from scratch. In the previous lecture, we looked at the applications of regression trees and we saw that they are much better than, let's say, ordinary least squares or other regression methods, especially at handling non-linear data. I also mentioned about the reference to the Stats Quest channel from which I have constructed this series of lectures. So let's get started with today's lecture in which we will learn step by step how to start building a regression tree. I predict that we will cover 3 to 4 lectures on this topic. Today is the first lecture. So please follow along and I hope that you like the lecture. So the problem which you are trying to solve looks like this. We have drug dose on the x-axis and we have drug effectiveness percentage on the y-axis. We have collected data for around 10 to 15 patients, and the data which we have collected is basically depending on the drug dose, what is the drug effectiveness percentage for that particular patient. And you can see this data has been plotted on the xy axis as has been shown in the figure. The goal or the objective which we have is that given this training data, we want to build a regression tree that uses a drug dose to predict drug effectiveness. Basically, let's say you have been given a new patient which is not in the training data, and you know the drug dose of that patient. Let's say it's somewhere here which is not in the training data. Can you predict what the drug effectiveness percentage will be for that patient? A classic regression problem, and we are going to solve this using regression trees. So that's the motivation, to give you a visual understanding of how the end goal looks like. This is how the final optimized decision tree looks like. And now we are going to start from scratch to build this tree step by step. There are many things, right? In this tree there is a root node, then there are terminal nodes, there are branches, there are leaves, and we need to make a decision on what should be there in every such node. As we did with classification tree, first we are going to start with root node. And what should be the correct value of the dose here in the root node? Why is it 14.5? Why not any other value, right? So that's what we are going to look at today. So as I mentioned, we need to decide the root node first, or what is going to come at the top of the regression tree. So I have written this as step number 2. Step number 1 was just being familiar about the problem, the end goal which we want to achieve. So in today's lecture, we are going to look at the specific objective of deciding the root node of the regression tree. So let's see how do we do that. So step number 3 is basically we need to calculate the average of the first two doses. You will see later why we do this, but the this step is that the initial thing which you need to do to find the root node is start from your data set and look at the first two values of the data set. So I have marked these values in this orange box, right? And then what you have to do is you have to take the average of the first two doses. So let's say the x-axis or the drug dose for this first point is x1 and for the second point is x2. So you have to take the average of these two. So I'm going to be doing x1 plus x2 divided by 2, which is equal to 3. And then what we are going to do is we are going to test with this as the root node. So this is how we are going to do this. So the average is equal to 3, right? So we'll draw a line here, a dotted line. Everything on the left side of this dotted line is for dose less than 3, and everything on the right side of this dotted line is dose greater than 3. So what we are going to say is that if for the patient the dose is less than 3, which means we are on this side, all we have to do is look at the number of points here on the left side. So there is only one point whose value is 0. So we are going to say that if dose is less than 3, the drug effectiveness is equal to 0. On the right hand side, there are so many points, right, which you can see in this blue dashed line. So we are going to say that if dose is greater than 3, which means if we are on the right hand side like this, we will take the average of all of these points, and that is going to be the drug effectiveness. So if you look at all these points and if you take the average, you will see that the average is equal to 38.8. So we are going to say that if the dosage is greater than 3, which means if we are lying on the right hand side, the drug effectiveness percent is the average of all of these y values, which is equal to 38.8. So the way this decision tree looks like is as follows. If dose is less than 3, if it's yes, we are going to say that the drug effectiveness is average of all the points on the left hand side. And since there is only one point on the left hand side whose value is 0, we are going to say that the drug effectiveness on the left hand side for dose less than 3 is 0. On the other hand, if we are in the no bucket, which means if dose is greater than 3, then we are going to take the average of all of the patients here on the right hand side here, which have been marked with this blue shaded region right now. We are going to take the average of all of them, which turns out to be 38.8. So if dose less than 3 was a root node, the way this will proceed is that if it's less than 3, we are going to say that the drug effectiveness is 0. If it's greater than 3, we are going to say that the drug effectiveness is 38.8. Now, this is just a trial, right? This is, of course, not the correct root node. So, we need to know whether we are moving in the right direction or not. So, there is this thing which is called measure what matters. Basically, currently, what matters to us is the root node, right? So, we need to measure whether this choice of root node or whether this decision tree is good or bad. And let's see how to do that. So this is a visual representation of what we are essentially doing. So we are saying that this orange line here is dose equal to 3. So we are saying that if dose is less than 3, then the decision tree predicts 0 for this point. And we are going to say that if dose is greater than 3, then the decision tree predicts this, which is 38.8. For all of these points, the decision tree will predict 38.8. Now take a look at the right hand side. So I'm going to call this RHS. Everything to the right of this orange line. Take a look at all these points. Now what I'm saying here is that for all of these points, I'm going to say that the true answer is this blue dotted line, which is 38.8. And visually you can see that it's a it leads to so much error, right? Because all of these points are diverging from 38.8. Maybe only this point has the correct value, but all of these points over here have a larger value than 38.8. All of these points here have a lower value than 38.8. So for all the points on the right hand side, this is definitely not the correct uh, value. So I have put a cross symbol over here. On the left hand side, we are actually doing quite good because there is only one point whose true value is 0, and we are going to predict the value to be 0. But it does not matter because there is only one point on the left hand side, and you can see that there are like 10 to 15 points on the right hand side, right? Which means for most of the points, we are getting a lot of error. So, qualitatively, visually, we can see that this decision tree is not doing a good job, and this is not the optimal decision tree. We move now to step number 5, which is quantification of this. So until now only qualitatively we have seen that this decision tree is not good, right? So let's try to quantify this. You If you have seen the classification tree tutorial, you must have seen that in classification tree we use a metric called impurity or Gini impurity, and that depends on probabilities. In the case of regression, this metric is actually something which is quite simple and easy to understand, and it's called as sum of the squared residuals, SSR. So sum of the squared residuals is the metric which will help us put this qualitative understanding into practice. So this metric will give us the power to assign a mathematical number to quantify how good or how bad our decision tree is. So let's see how this metric does that. Here I have plotted the same thing again. All the points on the right hand side of this orange line will get a value of 38.8. Now what we will do is that for each data point, we will see its true value. Let's say for this, the true value is 100, right? And we will see how far that is from its prediction. So this curly braces which I'm showing right now is the distance between the true value which is 100 in this case, and the predicted value for this is 38.8. So the distance actually signifies how much error we are making. So for this one particular point, the error is actually going to be 100 minus 38.8 whole square. That's the error. Now, if you look at these 3 points, this one, and this one, for all of them, their true value is equal to 100, right? But we are going to predict, our decision tree will predict that the value is 38.8 for all of them. So for all of these 4 points, the error is going to be 100 minus 38.8 whole square. Similarly, for all the points on the right hand side, we draw this vertical lines and we measure the distance and then we square the distance. That's the error. That's why it's called as the sum of squared residual. Why residual? Because it is the difference between the true value and the predicted value. And squared residual because we take the square. And why do we have the summation? Because we add all of these squared values together. So even for the left hand side, if you see, the true value for this point is 0 and the predicted value of our decision tree is also 0. So the error for this point is going to be 0 minus 0 whole square. So the way we will calculate sum of the squared residuals is that for every single point, we will first uh, actually write down the true value, which is what has been written here, and then we will be writing the predicted value, which is this. This is the value which our decision tree predicts. So you will see that only for the first point, the sum of squared or the squared residual for the first point will be equal to 0. But for all the other points, our predicted value is 38.8. So let's say for these 3 points over here, 1, 2, and 3, the actual value is 0, but the predicted value is 38.8. So the residual will be 0 minus 38.8 whole square. So this squared error will be added actually for all of these 3 points. So it will be 0 minus 38.8 whole square plus 0 minus 38.8 whole square plus 0 minus 38.8 whole square. So now what we are going to be doing is that we are going to add this error for all the points which are in the training data set here. So on the right hand side of this orange line, the predicted value is 38.8. So we'll subtract the actual value minus this and whole square. To the left hand side of this orange value, the predicted value is 0. So we'll take the actual value, subtract it from the predicted value and whole square. And we'll add all of these errors together. So this is what has been written in this mathematical representation over here. Now, when you add all of these different errors together, you will see that the sum of squared residuals is 27468.5, which is 27,468.5. It looks pretty high, right? But remember, we need to compare it to something. High and low is very comparative. Maybe it is the smallest residual error among all the errors. So that's why we need different points of comparison. But at least we have a mathematical number now. We have a mathematical number for the threshold of dose is less than or equal to 3. And now let's move ahead with comparing whether how this compares with other thresholds. So before doing that, first we plot a graph. On the y-axis of this graph, we have the sum of the squared residuals, which is also called SSR. And for the x-axis, we have the dose threshold. So currently we are starting with a dose threshold of 3, right? Which means that we are starting with dose actually less than 3. And for this, the SSR value is 27468.5. That has been plotted over here. So I am just going to be writing down dose is less than 3. The SSR value is 27468.5, which has been plotted in this graph. Eventually, this is that graph which will help us identify what's the root node which we should focus on. Great. Now let's move ahead. What we'll be doing now is, do you remember how we came up with dose is less than 3 as the threshold? We took the first 2 points and took their average, right? Now we have to do the same process for the next sequence of points. After we took the first 2 points, then we'll take the next 2 points. So this is what I'm going to show you now. We have finished step number 6, which is plot the SSR graph with the dose on the x-axis and the SSR on the y-axis. This step has been finished. Now we move to the next step, which is step number 7. Step number 7 is basically repeat the above same thing but for different dose dose threshold. So I'm going to show this entire process for one more dose just to make sure that you've understood what we are doing here. So now in this step we are going to take point number 2 and point number 3. Initially when we started we took point number 1 and 2, but now we are going to be taking point number 2 and point number 3. We take their average and it turns out to be 5. So then this is the threshold which we are going to try next. Dose is less than or greater than 5. So very similar to what we did before. What we are going to do is that we are going to have this orange line for dose less than 5. We are going to be looking at all points to the left. There are 2 points to the left and both their values are 0. So the average is 0. So we are going to say that if dose is less than 5, the drug effectiveness is equal to 0. Now we are going to look at all the values on the right hand side, which are all these values, and we are going to take their average again. It turns out that the average for all the points on the right hand side is equal to 41.1. So we are going to say that if dose is greater than 5, the drug effectiveness is 41.1. And if dose is less than 5, the drug effectiveness is 0. This actually leads to the construction of a decision tree for dose is less than 5. If dose is less than 5, yes, since the average on the left hand side is equal to 0, we are saying that the dose effectiveness is equal to 0. If dose is greater than 5, which means we are on this branch, right? And the average of all the points on the right hand side is 41.1. So we are going to say that the dose effectiveness is 41.1. This is the decision tree which is constructed for the threshold of dose is less than 5. Now, as I mentioned before, again we will be plotting the sum of squared residuals. So, what we'll be doing is that let me actually do a bit of uh, Control Z to make sure that these things on the right hand side, these lines are erased. Great. So, what we'll be doing here is that on the right hand side, the dose is saying 40, the drug effectiveness is 41.1, right? Which is this line. That's our prediction. So for all the points on the right hand side, we are going to predict this. And similar to the way we did before, we are going to find the difference between the true value and the predicted value for all these points. And then we are going to take the squared sum of these and we are going to add them. On the left hand side, the prediction is 0. So we'll do the same process, but it wouldn't matter because the true value is 0 and the predicted is also 0. So once you add them together, for all the points on the left hand side of this line, those less than 5, the error will be 0. But all the error will be coming from the all the points on the right hand side. So we'll be finding these distances, the residuals, we'll be squaring them and we'll add all of them together. And then we'll plot them on the SSR versus the drug dosage graph. So we had already plotted this SSR value for dosage less than or equal to 3, right? Now we plot the SSR value for dosage less than 5. And it turns out that the SSR value for dosage less than 5 is actually less than the SSR value for dosage less than 3. This is a clear indication that dose less than 5 is a better threshold. This is how you can compare now. This is the first comparison point. This is the advantage of SSR or the quantitative metric. Remember, we found this SSR value to be equal to 27,468.5, but we did not know whether it's high or whether it's low. But now we have a comparison point. We see that if we do the same thing for dose less than 5, the dose less than 5 SSR is lower than the dose less than 3 SSR. This is actually the first indication to us that dose less than 3 might not be a good choice for the root node actually, and dose less than 5 might actually be a better choice. So this is the calculation or rather the comparison for dose less than 3 and dose less than 5. And we have up till now, until this stage, determined that dose less than 5 is actually a better threshold than dose less than 3. In the next step, what we will be doing is that we will be sequentially taking the next set of points. So in this step, I have taken point 2 and 3, right? In the next step, I'll take point 3 and 4, then point 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 10, 11, 12, 12, 13. I'll find their average. like we did x2 plus x3 by 2. So I'll find the average for all of these points, and then I'll have that as the threshold of my dosage, and I'll find the SSR values for all of those. So I won't go individually to how it is done for each of these dosage, but I'll show you the plots. So the next, so after we did the SSR calculation for dosage less than 5, which shown right over here. Then we move to SSR computations for dose less than 7, dose less than 9, dose less than 14.5, dose less than 26, all the way up to dose less than 36. For all of these, we will be plotting the SSR values. But let me first show you how these different things look like. So for dose less than 7, for dose less than 7 on the, so this is, so let me write 7 here. So on the dose less than 7, on the left hand side, still the error is 0. But on the right hand side, you will see that the error is slightly a bit better, or the error is reduced. You can already see from here that when this blue line kind of becomes the average of all these points, that's when the error will be the least. So that's what we are looking for. So this is dose less than 7. If you now look at dose less than 9, it also leads to a slight decrement in the error. On the left hand side, the error is still almost negligible, but on the right hand side, you can see that this line, right, is moving up. It was at 43.7, and now it has moved up to 47. So it's kind of getting close to the average, to the real average value of all the points on the right. And the best error is obtained for the uh, dosage threshold value of 14.5. So I am just mentioning that over here. This is the value for which the best or the least error is seen on the left hand side as well as on the right hand side. So here you can see on the left hand side there are few more points here, and then this blue line is almost at the average, and on the right hand side this is dosage equal to 52, and we can see that this line 52 almost lies at the average of the y values of all of these, and that's why it actually leads to the lowest amount of error. If this blue line was somewhere very far below or very far higher, then it would lead to more error, because we are taking the square root of the differences. If you can similarly do the plots for dose less than 26, and you can do the plots for dose less than 36 as well. In fact, what I will do is that as the homework assignment, if you are watching these lectures and if you are following, I would highly encourage you to go back and make similar plots like this. Find this value, this average value for dose less than 26 and dose less than 36. This will make sure that the concepts are clear. Next, what we do is that we actually plot the SSR values for all these different doses. Dose less than 7, dose less than 9, 14.5, 26, 36. So let's plot them together. So this is the final plot which is going to help us choose the root node. So remember we started with, so let me actually switch the color to maybe light orange. We started with dose less than 3, then we moved to dose less than 5, then this is 7, then this is 9. So this value right here, right, this corresponds to a dose less than 14.5. And if you look at the SSR value, this is the lowest SSR value, which is actually just less than 15,000. And if you go beyond 14.5 on this side, you will see that the SSR values are higher and they kind of show an oscillation like this. But it doesn't matter now, because the only thing which we need from this plot is the point which shows the lowest SSR values. And that is clear. That is for a dosage value of 14.5. So dose less than 14.5 gives us the lowest SSR, or the sum of squared residuals. And that's why we choose this to be our root node. That's the real reason why dose less than 14.5 is chosen as the root node. So now, if you go to the start of this lecture, I showed you the optimized tree, right, which we want to end up constructing. Let's look at the root node of that optimized tree. So if you look at the, yeah, this tree right over here. If you look at this tree, and if you look at the root node of this tree, you will see that it contains dose less than 14.5. And now we have actually understood how come we decided this value among all possible values. There is a very clearly defined mathematical procedure to actually arrive at that value. You have to find the sum of the squared residuals for different thresholds of dosage, and then you have to plot the sum of squared residuals as a function of the dosage. So on the x-axis here, actually we have the dosage. So let me just write it over here. On the x-axis we have dosage. So you plot the SSR against the dosage, and if you check the dosage which gives the lowest SSR. So here it turns out that dosage less than 14.5 gives us the lowest SSR, and that's why this will be our root node. So up till now we have reached this stage of constructing the decision tree where we have finalized the root node, and that will further split into two branches, yes or no. Even this small step of finding the root node, you see we have covered this in 8 steps. So the logic and the understanding behind this is fairly detailed, but if you understand it once, then it will be very easy. What I have seen is that many students actually go directly to Python, they import the scikit library and they load the regression tree, but they don't know how root nodes are calculated, what the sum of squared residuals is, etc. As you can see, I'm constructing these lectures so that you can visually understand, but also you can see that everything is built from scratch. I don't want you to assume anything. We will of course be showing Python coding in this part also, but I want to supplement it with this detailed understanding from the basics. I hope you are following this series. I would highly encourage you to make notes as you follow this series so that the understanding is strengthened. Please ask in the comment section of YouTube if you have any doubts or if something is unclear. Thank you so much everyone, and I look forward to seeing you in the next lecture.